Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be looking at one of the major differences in between enthalpy and entropy. Because in entropy, it turns out it's actually possible to perfectly determine the entropy of a system, the absolute entropy of the system. That said, let's go ahead and start by really kind of refreshing everything we've learned so far about looking at changes in entropy. So if I'm trying to go ahead and look at a change in entropy, we can do so by looking at how that heat, or specifically the reversible heat, changes over the temperature. Now, one of the problems we end up having here is that we need an expression for the heat, specifically as it changes with temperature. We need this relationship. But that's where we can go ahead and fall back on our second chapter where we showed that the heat is going to be related to the heat capacity times dT, which means that it's actually going to be possible to go ahead and integrate over the temperature from whatever our initial conditions is to final to go ahead and figure out the change in entropy. Now, we're often going to assume that we're looking at relatively small temperature ranges at which the heat capacity is going to be fixed. Note that if this is not the case, then we'd have to do the more laborious exact integral to get the full definition. But for most cases, we can go ahead, pull the heat capacity out, and show that the entropy is going to be related to the heat capacity times the natural log of the ratio of the temperature change, with again a greater temperature difference, leading to larger changes in entropy. And that also means that if I know the initial entropy for a system, I can go ahead and figure out the final just by adding in the product of this integral. Now, one of the issues that we're running into is note that here we're using the heat capacity. But as we learned in chapter 2, there's multiple different heat capacities I can use. So which one should I use? Now, being chemists, we like constant pressure conditions. Specifically, we love 1 bar. So that means we get to use our isobaric conditions. So we're going to go ahead and use the isobaric heat capacity. So if we know our initial temperature, our final temperature, our entropy at the initial temperature, and the heat capacity for that range, we can figure out the final entropy for any sort of heating process. Note, we can also do this same process for isochoric conditions or constant volume, simply by substituting the isochoric heat capacity. Now, one of the reasons why this is very nice is that now we have a good idea of how entropy changes with pressure, temperature, and phase. That means that if I'm doing a more complex change, I can add together each of these individual bits. So for example, let's say I'm going from a solid to a gas. Well, now I've got a slight issue because if I'm going from a solid phase to a gas phase, that's a lot of changes. I have to figure out how the entropy changes as I heat the solid, how the entropy changes as I undergo the phase change, then I heat the liquid, then I vaporize that liquid, and then I heat the gas. Now, here's the important bit. If you're looking at a more complex process, just like we saw with enthalpy, don't try to do it all at once. Break it down to its individual bits. So if I'm trying to figure out how the entropy changes as I'm heating a solid, well, congratulations. I can just take the integral of the heat capacity of the solid, which again should just be the heat capacity times the natural log of whatever my initial temperature is to that melting point. Then phase changes are actually a little easier. We can literally just look up the enthalpy of fusion or vaporization and then just dividing by the relative temperature of transition. So for melting points, it's going to be enthalpy of fusion divided by the melting point. And for vaporization, that's going to be the enthalpy of vaporization divided by the boiling point. Now, if I'm looking at going from solid to gas, note when I'm heating the liquid, I'm going to do this over the entire liquid range. So that will mean I'll take that integral from the melting point all the way to the boiling point. And then if I'm heating the gas, I'll eventually stop at some temperature I care about, but we'll go from the vaporization to whatever that temperature is. Now, note, this is just a generic process going from solid to gas. Sometimes I might want to go from solid to solid, so I'll only use that heating term. Sometimes I'll care about going from solid to liquid. So I'll use the heating of a solid, uh, the melting of the solid, and again, the heating of the liquid. So you can always just use the portion we care about and just add together those terms. And this is really powerful as so many of our processes are not just going to be simple one process, but maybe combined. For that, we get to use the beauty of state functions and add them together. Now, there's important corollary as we're changing all of these conditions. And that's the idea that the system's going to keep losing entropy the more I cool it. So the more I cool it, the less movement and the less states it can occupy. And that leads us to a very important question. How much thermal disorder am I going to have at 0 degrees Kelvin? So the idea is at 0 degrees Kelvin, the system should stop moving, which means there should be no thermal disorder, which means that entropy is going to start to approach zero. And this is given by the Nernst heat theorem, which says that as I cool the system to 0 Kelvin, the entropy should approach zero. Note it does not say that it equals zero, because there's an important caveat here. And this is the Nernst heat theorem can more or less be summed up in the third law of thermodynamics. And that's the idea that the entropy of a perfect crystalline substance at 0 Kelvin will be zero. So essentially, we should have removed all of the entropy from disorder. That means we can only be in one single state. Because if I have a perfectly crystalline substance, that means that everything only has one microstate. And if it has one microstate, the entropy is zero. Because we can't excite it to any elevated states. Now note, there will be some substances that do have a non-zero entropy at 0 Kelvin. There are going to be states where there's multiple different crystals, or the crystal itself isn't perfect. So for something like ammonia, there's different ways I can arrange the ammonia lattice, so it has an entropy, I think, of about a half. But notice the entropy still approaches zero, meaning that both the Nernst heat theorem and the third law of thermodynamics generally holds. But most substances will tend to adapt perfect crystals at 0 Kelvin, which means that I know the absolute entropy of a system. And then if that means as I heat it up, it's possible to determine the absolute entropy, not just the relative entropy for a substance. So that means I can try and figure out the entropy of a substance at any temperature. But to do so, I have to know how the heat capacity will change as I go from zero all the way up to the temperature I care about. There's a slight problem in that very low temperatures, because of quantum shenanigans, that heat capacity gets a little bit weird. And its behavior isn't necessarily what we'd expect at higher temperatures. Specifically, the threshold here is about 20 degrees, 15 to 20 degrees depending on the material. And it turns out under these low regimes, the heat capacity follows something called the bias extrapolation, more or less that it follows a cubic law as a function of temperature. So as the temperature doubles, that means that the heat capacity would go up eightfold. Now, mind you, it only does this for a very narrow regime, but that also means that the heat capacity changes very greatly over these 20 degrees. Now, to do this, we also have a coefficient that needs to be heat fitted. So this is this A parameter. The only way to determine this is through experimentation, but if you have it, then you can figure out how the entropy changes as you go from 0 to 20, and then from there you can use the normal heat capacity. And so you can use this to go ahead and combine with our normal entropy differences to figure out the absolute entropy of a substance. So instead of now going from figuring out the entropy difference from some T1 all the way up to a final temperature, we can figure out the total entropy, or the third law entropy, also known as the absolute entropy of a gas, by simply starting with the entropy at 0 degrees, often going to be zero, but not always. Then we'll add in the Debye extrapolation. So again, we'll go ahead and integrate it. Note in the integration, that would be a to the T2, which will integrate as to T3. So then when you go ahead, that will get you to about 10 to 20 degrees, at which point we can now switch over to using the solid heat capacity. Again, over larger temperature regimes, you're going to want to use a temperature dependent heat capacity. And then again, as normal, enthalpies of fusion, heat capacity for the liquid, enthalpies of vaporization, and heat capacity of the gas. So using this, it's entirely possible to determine not just a relative entropy, but the absolute or third law entropy for any substance. And when you look in many different tables, this will be the value you'll actually find. So next time, we're going to be making use of these third law entropies to figure out something we really care about, the entropies of reaction. Until then, take care.